All right, folks. This is about the third or fourth time that I've tried to complete this this third segment video for section 5.1. I've been having some trouble with file storage and uploading those files to Blackboard. So I'm going to try something a little different. I'm going to try to use the Zoom functionality for cloud storage, and then hopefully this works. I'll provide a link on Blackboard, which if you're seeing this, it obviously works. So. Anyways, where we had left off was we had talked about both the fundamental identities, just sort of a catalog of them, and then we had looked at simple problems involving, if we know one trigonometric function, how to find the value of another given a quadrant angle. Now we've done that problem before. It's been a while, but we've done it before. And what we were trying to do there was really develop these sort of the preliminary bits of these proof techniques in the context of a problem we'd already seen. Now, what we're going to do with this remainder here, which I'm pretty sure I can finish out the section here, is that we're going to look at some things that very specific tasks of trying to transform expressions from one thing to another. And part of that is an extension of what we did before. Okay, so I'm going to switch over to my document camera now, and we will. You'll see that I've already got everything printed up because I've done this a couple times, and I've already managed to upload the pages to Blackboard. So I don't really want to go do that work again. Okay, so starting on page 6, then section 5.1. The statement of a problem we might be interested in, and this is something that we've done previously but wasn't really written in this context, is to say, okay, let's see if we can write an expression for one trigonometric function as a function or in terms of another trigonometric function. In this case, write cotangent of x in terms of cosecant of x. Now, for some reason, there's a little bit of confusion about this sometimes on the part of the student. What this means is that our end product is going to look like cotangent of x equal a bunch of stuff that maybe has cosecant in it, but no other trig functions. It certainly doesn't have cotangent in it, right? So this is the whenever you see that is the goal, right? This in terms of that, you should end up with something that has this equals a bunch of stuff involving that. So here's the thought process that goes into this is, well, we already have a trigonometric identity, one of the third Pythagorean identity specifically, that relates these two. Now, it's not cotangent equals, but that's where we're going to start from, is the third Pythagorean identity, right? So cotangent squared x plus 1 is equal to cosecant squared of x. We'll do a little bit of algebraic manipulation. We'll move the 1 to the other side here, and then we take the square root of both sides. Notice that introduces this plus or minus. You're going to see that a lot, and we've already seen it a lot, but in general, it's not the worst thing in the world to have a plus or minus, but it actually says there's two different expressions. So the final result is the cotangent of x equal plus or minus the square root of cosecant squared minus 1. Which tells you that if you know the value of cosecant, you can do this arithmetic and you can find the value of cotangent in a concise formula where you don't have to know, you know it in general as opposed to for one specific value. Okay, so let's go a little bit further here and do one that's a little bit more challenging here because it involves more than one identity, fundamental identity. Write cotangent of x in terms of sine of x. Now, you could do a lot of different things here, and don't think that there's one way to do this. But since we've already kind of done a little bit of the legwork here, I would recommend starting from right here and making a substitution for cosecant, and then manipulating this so that it's in a form. Because at that point, we'll have wiped out all the cosecants, and all we're left with is sine and maybe some numbers like 1 or 1 over or whatever. So that's exactly what I've done. Is I've substituted for cosecant 1 over sine. Again, that's another fundamental identity. And so what you're seeing is that to be able to write whatever trig function in terms of another may use, in the case of this one, it may only use one identity with a little bit of algebra, or it may actually use 2. There are actually cases that use 3, and you know, they don't get much more complicated than that. This is sort of about a middle grade problem because you need to use 2 different identities. This maybe is a little bit on the easy side, but I think you get the idea. So what we're left with is this expression. However, as you know, there are some rules of simplification, and we do need to adhere to those. And this is exactly the case. We can't have this bizarre looking expression under the radical. So we do a little bit of a manipulation here. I'm going to try to find a common denominator, which is sine squared, and then add those 2 terms together. And then finally, I'm going to break apart the radical and have just sine of x in the denominator. So the net result is that cotangent of x can be written solely as a function of sine of x, and that is plus or minus the square root of 1 minus sine squared of x divided by sine of x. Okay? So that's kind of there's some exercises in the textbook that I've assigned for this that are more or less about this kind of level of difficulty. Take a look at them, practice them. I probably will ask a question like this on the test at some point, which I haven't really quite figured out exactly how that's supposed to work. But anyways, okay, so let's move on to a more interesting class of problems, which are starting to get a little bit closer to what we would consider to be a true identity. Yeah. So in this particular case, rather than just blowing it all out, I'm gonna give some specific requirements here. So what we're gonna do is we're gonna start with an expression, and we're gonna be asked to rewrite the expression in terms of sine of x and cosine x only, with this further expectation that there be no quotients left. Now, I'll say this. I pulled this statement straight out of the textbook because this is the way a lot of the problems are set up. However, the textbook doesn't actually follow its own rules. So what ends up happening is that this quotient business, removing all quotients, isn't necessarily even possible. And so I don't want you to fret too much about that. I think as long as you try to simplify things to a certain extent, you will not be able to remove all quotients. It's just not possible. So let me start with this example. I've got about 4 of them. Here's an expression, tangent of x times cosine of x. And what we want to do is we want to turn this into something that only has sine and cosine in it. So get rid of every other kind of trigonometric function besides those 2, and then we do as much simplification as possible. That is an incredibly important skill. I want you to understand that. And it's not just for practice here, but this is something that you'll probably do in a calculus class for the rest of your life. So why sine and cosine? Well, you can express every trigonometric function in terms of just sine, any one trig function, but there is some convenience to be able to use 2. It tends to remove a bunch of these radicals if you can use sine and cosine. I guess the same can be true for secant and cosecant, or even tangent and cotangent, but I don't think that, you know, if you got to settle on 2, sine and cosine are the ones. Okay, so one strategy for these kinds of problems, and there are several of these, is to start by saying, well, we already know that there's a way to write every trig function as just a combination of sine and cosine, and then work towards simplification from there. So that's a very common first strategy, and I'll show you that as it happens here. So first, I did exactly that. I substituted tangent of x for sine over cosine. And this is where we're going to start adding in the justification for this, the class of fundamental identities we use to justify this step from here to here. This happens to be a quotient identity. Now, you should be able to see pretty quickly that algebraically speaking, we have cosine in the numerator and cosine in the denominator. That's going to cancel. And what we're left is just simply sine of x. So this expression equals sine of x for all values of x that are in the domain of all three of those functions. And notice here on the right, I've put as a justification algebra. This is not an algebra class. I'm not asking for which specific property of algebra allows you to do this, blah, blah, blah. There's a lot of manipulation that we do that is actually algebraic, and I don't necessarily need to see all those steps. It's the trig steps that are really more interesting to me. Okay, this one is relatively simple. Let's make one a little bit more challenging. Here we have cosecant of x times cosine of x times tangent of x. Well, that strategy before worked pretty well. Why don't we just try that again and write all of these terms, unless they already are, let's write them in terms of sine and cosine. So cosecant will become 1 over sine, tangent will become sine over cosine, and this is exactly what I've done here. I've got 1 over sine, cosine, sine over cosine. And notice I've put the justification RQ. I've kind of doubled up some things, and this is pretty common when you're doing this sort of step, is to say, well, let me just start by turning all these into sines and cosines. And those almost universally use so-called reciprocal and quotient identities. I'm willing to let it slide. You should probably be doing those as separate steps, but it happens so often that I'm willing to cut some people some slack. So now, looking at this expression, you can see that there's a lot of things that will cancel here. We've got sine in the denominator, we've got sine in the numerator. Here we've got cosine in the numerator, cosine in the denominator. So these are all going to cancel out. What we're going to be left with is 1 over 1 times 1 times 1 over 1, which is really very uninteresting and just equal to 1, right? The justification for that is simply an algebraic process, which I forgot to put here, but I probably should. Algebra. But that's, I mean, really, at some point, we're not baking sourdough bread here. Okay, so let's try another one. I've got 3 more on the next page. Let's try one now that is they're starting to get a little bit harder. And maybe some different techniques will come in as we see them. So let's try this one. How about cotangent squared times the quantity 1 plus tangent squared of x. Sorry, I really should be saying that. Cotangent squared of x times the quantity 1 plus tangent squared of x. So one thing to observe here is anytime you see something like this that looks like it might very well be an application of a Pythagorean identity, usually I just do that first. I say, look, I can simplify that into a single term. And so I'm going to go ahead and pull that first. The 1 plus tangent squared x is equal to secant squared x by a Pythagorean identity. In fact, the second Pythagorean identity. Now, you could, at this point, turn all of these into sines and cosines, just like we've done before. But I want to pause a second, because this is something that's often overlooked, is that cotangent by the quotient identity has something that relates to just secants and cosecants, right? It's going to be cosecant. Cotangent will be cosecant over secant. So cotangent squared is cosecant squared over secant squared. And I'm using that to get rid of this term right here, this secant squared. So I'll make that substitution. Here I've got, by the quotient identity, one of the quotient identities, cotangent squared is equal to cosecant squared x over secant squared x. And now, this is going to cancel with this secant squared. And what we're left with is just simply a cosecant squared, which, using our reciprocal identity, will be 1 over sine squared, which, you know, accomplishes the goal in that we only have things that are sines and cosines, but notice it has a quotient. And so these instructions aren't very clear. It doesn't really make any sense, because there's no way, I will assure you, there is no way to write 1 over sine squared using only sine and cosine where you don't have a quotient, right? So it's kind of a little baffling. And I wanted to point that out because the homework problems in the textbook sometimes fall prey to the same mistake. And I'm not really sure what they're doing or why they do that, but it's something to be aware of. And I actually wrote some explanation of one set of problems. I think it's in 5.2 that when you're trying that stuff, read that carefully. Okay, on to problem number 4. This one's starting to look a little bit more complicated. I got a little tight on my page, so I started writing a bunch of stuff a little bit more compact. Didn't want to go on to a 9th page because it's a little bit challenging to get these things uploaded to Blackboard. Anyways, so if we start with this expression, 1 plus cotangent of x over cotangent of x. Now again, we could just go back and substitute everything in with sines and cosines and follow some pretty basic sorts of techniques. But I want to show you, I want to, at this point, I want to be showing you stuff that's next level, okay? And so when I see something like this, I'm saying, I'm thinking to myself, well, you know, there might be a way to simplify this without doing any kind of trigonometric substitution. I can just separate these out into 2 different terms, and I'll get this cancellation, cotangent over cotangent. Now be careful, because what I see a lot of algebra students, and this is really something that I have to harp on people when I'm in an intermediate algebra class, is that there's this, I don't know why, people don't know how to really work with rational expressions, okay? And what they'll try to do is just cancel that cotangent with that cotangent, and be left with 2 or 1 or some other kind of dumb thing like that that's not really true. What you can do, though, is you can split these into 2 fractions, okay? And this is actually, you know, I'm trying to be real meticulous with each step, and this will actually lead to some simplification that's pretty useful. So as you'll notice, cotangent of x over cotangent of x, well, that's going to reduce to 1. And sitting right here, 1 over cotangent of x, well, that's tangent, right? So that's my next step, is to just simply write this as tangent plus 1. Tangent of x plus 1. Now, this is an application of both a reciprocal identity and also an algebraic series of steps. So I'm still trying to justify those, which it is good practice to do that. You really should know why things result from one to the other. And so now what I'm left with is a need to transform this into only sines and cosines. Well, there isn't much to be done. You simply use the one of the quotient identities and transform the sine of x over cosine of x plus 1. Again, you have a quotient, though. And there is no way to get rid of it, so the instructions that were given for the problem really don't make sense. But I think we've accomplished what they were asking, to the extent that this is a simplified expression. And that's really what this is. It's veiled. It looks like you're doing something, you know, sort of like, why are we doing this? You know, what's this process all about? But the reality is that this is the rule, quote, rules for simplification for trigonometric expressions. There aren't really rules, but there are some targets that we'll use later on. This task of turning things into sines and cosines is actually a really powerful technique of, quote, simplifying a trigonometric expression into something that's relatively simple. Now, it's not actually simplification, right? Like you have with radicals or something along those lines. There are actually pat rules in algebra, but in a trig setting, there aren't really rules, but there are strategies to get you to certain points. Okay, so anyways, let's start with the next one, and I want to introduce something where we start messing around with the argument a little bit. This is going to be certainly not very heavy, but let's start with this expression: tangent of negative x over secant of x. Now, when I see this, an argument that's got something weird, I'm almost always going to make a substitution for that to turn the argument back into something I'm a little more comfortable with. That's almost a universal truth when it comes to a proof, is to say, well, you know, I'm going to have to get these to look the same at some point anyway, so why don't I just do it right from the beginning? And anytime you're dealing with negative signs and arguments, you should be, you know, red lights should be going off. You're thinking, oh, that's a symmetry identity. So since tangent is an odd function, the negative sign will actually pop out. And that's exactly what I've got right here. We've exchanged the negative argument with a positive argument, and the negative sign has come out, and that is, of course, a symmetry identity. Now, at this point, you could go a couple different ways. As with every trig proof, almost every one of them. There's many different ways to get to the final result. So I'll just do the one that feels the most natural and probably would simulate what you would be doing, which is say, okay, well now I've got these expressions, neither one of which are sines and cosines. Maybe I just transform them into sine and cosine, possibly ratios or whatever, using reciprocal and quotient identities. And that's exactly what I've done here. I ran out of space a little bit because I really am at the end of the page. Reciprocal and quotient identities lead to this result, which is that tangent becomes sine over cosine, secant becomes 1 over cosine, the negative sign, don't forget those, it's easy to like lose them. And now I have what's called a complex fraction. I've got a fraction inside of a fraction. Certain standard techniques, notice these fractions inside the fractions both have the same denominator, and so that'll simply go away. Through a little bit of algebraic manipulation, we end up with a final expression of negative sine of x. So the net result is that our original expression is actually equal to negative sine of x, and that is an algebraic state. So I'm gonna cut it here. This is the end of section 5.1. As I said, I'm still working with our technological limitations and whatnot, and so hopefully that gets better the longer that we go on.